our presentation for ME106, our project, we made a 2-axis camera stabilizer. Group members are Justin Wayne, Gavin Ganad, Matthew Erdenibeleg, and Alec Lefteroff. So for our project, we made a 2-axis stabilizer using 2 different actuators, or sensors, and actuators. The external conditions were measured by a gyroscope, which are when we turn the camera left to right, up and down. And the internal conditions are calculated by the joystick, where we choose where the direction wants to go. This is a hardware overview for our project. We have the gyroscope, 2 servo motors, the joystick, and it's all connected to a breadboard connected to a Raspberry Pi Pico. For the logic for the code, we took the gyro data, we calculated the pan and tilt, we put that into the PID as the input, and then for the joystick, we use that to map a target pan and tilt so that the camera just stabilizes to that value, and we put that for the PID set point, and that PID turned out data for the motor command.
For the gyro calibration, we measured the noise in the gyroscope, and we find the average over 5 seconds. This information gets applied to the gyroscope data during the main control loop to offset the noise. And then that final gyroscope data is integrated over time to calculate angular position.
Using time integration, we calculated the angular position because the gyro gave us an impulse value, so integrating gave us the overall position change. So for the target position, we used a joystick. So we mapped the joystick to hardware orientation. We limited the change in target orientation, and we limited the speed, and gave us a set point.
For the PID, we use a proportional gain of 1.0, an integral gain of 0, and a derivative gain of 0.3. We set our limits for the PID to 90 degrees, and here we have the PID set up, inputting the proportional, integral, and derivative gains, having the set point be 0 as that is the initial target point. Our scale is in seconds, and then the output limits are the plus or minus negative 90 degrees. During the main control loop, we call the PID as dpan and dtilt in order to calculate the motor commands.
Here we have the move servo function, which uses the map value function to convert the desired angle to the required duty cycle. In the main loop, the move servo function is called to the dpan and dtilt angle with an offset of 90 degrees to represent the middle of the servo position. Okay, here is the demonstration of our 2-axis stabilizer gimbal. So right now it is calibrating, and calibration is now complete. So this is us testing the target set with the joystick, seeing the panning, now the tilting. Now it's testing the gyroscope and the stabilization using the panning, and then now the tilting. Here are the project's significant hurdles. The plug-in style of wiring induces significant impedance in the system, so the mechanical movement of the system often causes an I2C communication failure. We also used the raw gyroscopic data without converting it to a format that was useful to our needs. The noise in the gyroscope would cause the calculated angular position to drift over time. During the troubleshooting, we often found that the sensors and motors were often mismatched, so the variables were rewritten to consistently say pan or tilt. The servos often start to rapidly oscillate during operation. We believe that this is a PID tuning issue. Here are the steps we could take in the future to improve the stabilizer. You could splice and solder the wires to improve connection, using 2 different gyroscopes for pan and tilt to improve destabilization when both adjustments are needed. Tuning the PID values require knowledge of control systems that our team currently does not possess. Utilizing the joystick switch to reset servos and gyro to the set position at the start of the program, and overall refining the code to run more efficiently. And here are the libraries that we used for the gyroscope and the PID.